Today with generation, first let's define what I mean by thermal generation. We've been talking about it just like kind of sporadically, but let's actually get into it. So today we're going to go through how you derive equations that involve thermal generation, and we'll go through hopefully an example at the end. Okay, so thermal generation, I guess the definition of that is that there's some material, again we're thinking about a conduction problem here, so think of a solid material. So there's some material in which there's volumetric addition to the control volume. So think about that, right? There's, over the entire control volume, there is a conversion of energy from one form into heat. And that effectively adds heat or thermal energy uniformly in the control volume. This is different from ideas like a heater, right? So let's maybe sketch some things out here. So let's take this block, and on the side of this block, I'm going to put a heater. And I'm going to say that coming in here is some Q dot, right? That Q dot is adding heat into the block here. This is not volumetric generation, right? This is something that's occurring at the boundary of the domain. Let's say we're modeling, right? We're modeling this guy here. It's occurring at the boundary of the domain. It's a boundary condition. You have a specified flux or a specified power coming in. It is not volumetric generation. Now, if we were to actually model this heater, so let's kind of blow that up. Let me pick a different color, sorry. So let's actually model this heater. All right, so this thing here, and look at a control volume analysis within the heater itself. Now, there's maybe uniform generation across this entire thing. So like there's energy being converted from electricity into heat. So that is volumetric generation. We normally describe the generation inside the domain in terms of this coefficient G dot triple prime. So this is effectively the watts that are being generated per unit volume, right, per meter cubed. And this is going to be, some value greater than 0 in this case. All right, so generation can have some spatial variation with it. Like you might say G dot triple prime is actually a function of x, y, and z. But let's start off by just saying it's like spatially uniform, and that there's a single coefficient that goes with our analysis. So maybe while we're thinking about this, I've given you the example of a heater, but maybe there's other examples that we can think of. Any examples come to mind for generation? Say it again? Yeah, so like chemical, right? You have like breakdown of, so let's call that chemically reacting media, right? So in your stomach, you are converting food into energy, basically, and it's releasing energy. Any other examples? Yep, radioactivity, right? So think of a nuclear reactor. You have decay of elements. It's converting from potential inside the atom or electron shells down, or splitting of atoms. Anything else? Other examples? Okay, I'll give you a few. So nuclear reaction, chemical reaction. What about like glass in a window? It's absorbing energy from the sun as it passes through it. So absorption of radiation. Right, that's within the volume. There's some transparency, light's coming in and being absorbed volumetrically. Other examples, viscous shear, form of friction. So we won't deal with that because that's in a flow, right? We're going to only talk about conduction problems, but that's an example. Another big one is electrical dissipation. And so that one comes up a lot, right? You have, as mechanical engineers, you're often working with devices, motors and such. And you have to deal with the heat coming off of that. So there's a relationship there you should remember. Let Let me just write it down. So G dot is equal to current squared times the electrical resistivity, RE. Just remember that one. There's kind of different forms that takes. Gas compression, some other stuff comes up, but these are examples, right? This is the generation idea. Let's actually go through and do an analysis that derives the equations for this then. Remember back to the simpler case where we don't have generation. There's these steps that we went through. I've outlined these steps here just so you don't have to write them down, but they're things we've already talked through. So we're going to define the domain. In this case, we have our domain from 0 to L. So this is like some block or some wall or something, a plain wall we're going to analyze. Second thing is we're going to draw our control volume. I've already done that. Again, we're thinking about 1D, right? It's still 1D conduction. So, and you see that the differential width in that x direction is a finite length, right? Like this width here, oops, sorry, this width here is dx. So there's only that differential width in the direction that heat is conducting. In the other direction, in y or in z, we fill the entire domain. Okay, perform a control volume energy balance, determine what's going in, what's going out, rate equations, solve for t, and then apply boundary conditions. So it's the same procedure that you're becoming familiar with, but now we have to introduce this idea of energy generation. So let's kind of fill this in a little bit and make sure we kind of understand what's going on. So let's do the control volume analysis. We have our differential width dx. We have to deal with what's going in and what's leaving. So going in is q dot at some coordinate x. What's leaving is q dot at x plus dx. We could have up here, in the control volume, we could have du dt. We could also have g dot occurring. This is a steady state problem. Let's keep it as a steady state. So this goes away. But now we're left with this g dot, right? This is new. Right? This is part that we haven't dealt with before. So let's figure out how to deal with it. All right. So we have our energy terms. Let's do the control volume energy balance. So remember, just generally, we're going to say in plus generated is equal to out plus stored. In this case, we don't have any stored energy, but this yields, for the specific terms that we had, it was q dot x plus now this generation term. So we have g dot, but let's maybe be a little bit careful here. So we're going to assume for now that g dot is like spatially uniform. That is, there's no variation in coordinate x with the generation. So we can describe g dot in terms of g dot triple prime, but the units on q dot are watts, right? The units on g dot triple prime are watts per cubic meter. So we have to introduce something about the volume of this differential control volume in order to deal with the unit mismatch. So we're going to multiply by the volume. Right, looking at the control volume that I drew up there, let's call this, here, let me do this. So I'm going to draw this green line here. This green line into and out of the page, let's call this cross-sectional area AC. Right? This is the area that's available for conduction to flow. So what's my volume? Right, yeah, go ahead. Yes. So the answer is AC times dx. Right, this is kind of when I write it down, it's obvious, but it's subtle. So there's a differential volume that goes with this. AC is a constant. Dx is differentially small. You have to keep track of that dx because it becomes really important in future steps. Question?
So the AC is like the slice of paper?
Yep, so the question is what is AC? Again, this is the biggest source of confusion, I think, for for heat transfers, like what is this cross-sectional area? So think of it like, going back to the resistance model. The resistance model says I have some potential, TH and TC, and I have some heat flow. The area that's available is proportional to the resistance, right? So if I contract everything down to this really small bottleneck and I'm trying to flow everything through that, the impedance goes way up, my resistance goes way up, right? So think of the area, the cross-sectional area that's available in terms of that impedance model. So that's the long answer. The short answer is yes. It is the area that's available, like as you're moving in the x direction. So you're moving in the x direction, you see that there's a width into and out of the page in the z coordinate, and there's a height in the y coordinate. The cross-sectional area is that height in the y times the depth in the z coordinate. Okay, so we have started our control volume. We still have some stuff to do. So we have the generation, and then we have to look at what's coming out. That's just q dot at x plus dx. Okay, so now we're going to find the heat flow as dx goes to 0. And remember what that means is we're going to take that Taylor expansion model and plug it in. And let's do that. So this looks like q dot x plus g dot triple prime ac dx is equal to, now we expand out the right-hand side, q dot x plus dq dot x dx dx. All right, q dot x, this one that's hanging out here, that goes away, right? That's just equal on the opposite sides. Now we have this g dot triple prime ac dx plus dq dot dx dx. Remember last time we've done this, or every time we've done it, we're just having this dq dot x dx dx equals 0. But now because we have generation, there's something else there. It's not 0 anymore. That's saying the change in heat as a function of x is not 0. And that makes sense. There's generation occurring, right? But the important thing, aside from just conceptually understanding what's going on, is we can't be left with these dx's. So whatever you do as you go through this process, if you end up with this dx that's just left over, you've made a mistake, right? You always have to get rid of the dx in some way. Here it works because I guess we were kind of careful about it. The dx's cancel out, right? If it's different coordinate system, you're looking at dr or d theta or something like that, it doesn't matter. All those differentials have to cancel out. Otherwise, you can't solve the problem. Okay, so we're left then with our differential equation, which is dq dot dx is equal to g dot triple prime times ac. Again, it looks similar to what we had before, but now it's, instead of it being 0, there's a term there. And that changes the solution. It changes the answer. Okay, questions on this so far? The question was, is there a reason why I just wrote dq dot instead of dq dot x? At this stage, once you get past like that x dimension control volume, and you get rid of the differential and you sort of say things that dx has gone to 0, at that stage you can kind of drop it because it's no longer, it doesn't help you anymore. I guess you could keep it if you wanted. I'm a little bit sloppy about it, but it's mostly just to make sure that as we're going through it that I've noted that it's q dot at a position x, not at x plus dx. Right? So once we get rid of that bit, we're sort of safe. Okay, so then let's substitute the rate equation. Remember our rate equation is Fourier's law in the coordinate x. So we're going to do g dot triple prime times ac is equal to d dx rate equation minus k ac dt dx. Okay. You'll notice AC being a constant cancels out. That's good. It doesn't, you don't necessarily have to have that. Like you can still solve it like you did in the homework. You can have an AC that doesn't cancel out, but in this case it helps us. Let's also take this minus k and divide through. So let's put this over here. And so we're left with the differential equation in terms of temperature. So that looks like, this. D squared T dx squared is equal to minus G dot triple prime over K. Okay, so that's an important step to get to, right? You got to figure out what the governing differential equation is in temperature. From there, then we're going to solve this equation. So to the next slide. Find the solution for T. So this equation, again, is separable. Right? And hopefully you all remember what I mean by separable at this point, but basically we're saying I have two variables, T and X. In order to solve it, I need to separate them out, right? I need to have X on one side, T on the other. Here I can do that because I can take the dx and move it over and integrate and then do that again. If you had some function where you have like temperature by itself and then X is included in a separate term, that's no longer separable, and then you have to take different approaches. Right? Here it's separable because there's just this constant on the right-hand side. We can deal with it. So let's solve the equation. So let's take the integral of the differential dt dx equals, bring the constants out, minus g dot triple prime over k integral of dx. So that integral evaluates to dt dx is equal to minus g dot triple prime over k times x plus c1, our first constant of integration. Okay? Still separable. Or you can bring the dx over to the right-hand side. We have t on the left-hand side. So let's do that. So we have the integral of dt is equal to the integral of minus g dot triple prime over k c1 x plus, I'm sorry, what do I do here? Minus g dot triple prime over k times x plus c1, all that times dx. Hopefully I got that. Should be easy. Okay, so then this all evaluates to our general expression for temperature, which is T is equal to minus g dot triple prime over 2k times x squared plus c1 times x plus c2. Right? Our general expression. No boundary conditions yet, so it's not specific to our problem. In fact, we haven't actually outlined what the problem is, so I'm going to leave it here and not do the boundary conditions. But this is the general expression. So to actually finally solve this, you'd have to know the boundary condition on the left and the right, enforce those, and then get to the unknown constants.